Hey everyone, it's great to see you. Thanks for coming here today. So I'm Vlad, and I also want to introduce my two cats who helped me with this presentation. Especially, it's special for them because I get to visit their extended family here in Greece. They were adopted. It's a long story. They're a rescue shelter in the Netherlands. Somebody there went on a trip to Greece and took them back. And so their name is Alice and Orion. This is a baby picture of them, apparently, with a flag in the background. I think it's a nice opportunity to, if any of you have any of their families around, you can tell them we say hi. So today we're going to talk about structure prediction, about doing machine learning with structure in the inputs and structure in the outputs. You already have seen a bunch of the first stuff, so this is a bit of a recap. We're going to spend most of the time on so-called structured outputs. I'll say in a moment what I mean by that. Machine learning, which is sort of the paradigm or the field or area that we use very strongly in NLP today, is, if we were to put it in just a few words, the study of understanding, choosing, and designing machine learning models, learning algorithms to train those models, metrics to evaluate how well those trained models do, experimental methodology, and so on, that we use to learn and evaluate this sort of mappings from some inputs X, conventionally, to some outputs Y. Right, so we just use these letters usually, Now, what do I mean as structures? You're gonna run into a bunch of people who use different definitions for this term. So I think it's important for me to tell you early on what I mean by it. So a structure is the way in which the parts of some complex object are organized in relation to one another. Right, so when we talk about the structure of something, we talk about what parts make it up and how those parts go together, how they can or cannot go together and combine. Right? And in fact, many objects that we might want to do machine learning on, especially natural language processing, they have interesting structure that is important for us to use in designing our models. You can talk about machine learning for structures when looking at language, at images, shapes, networks, and all kinds of other things. So what I'm going to show you today is how to work with structure both in the input, so in the famous X, and also in the Y. Okay, this is like, in a nutshell, the summary for what's coming. If you're kind of like visually minded, this is the sort of things that I mean when I say structured objects, right? We can have sequences, which are a bunch of parts or variables that are linked sequentially one after the other, right? But also grids, this appear a lot in image processing. Graphs, you can think of them as a general case of sequences and grids, right? With various kinds of connections between the parts. Alignments, permutations, and hierarchy, these are some types of structures that you could work with. And we are in an NLP targeted school, so we should zoom in a little bit and talk about the kinds of structure that are most prominent in NLP, at least today. Right? So language, the way we speak it and the way we write it, is usually, typically, sequential, right? Words come one after the other, right? So we often encode language as a sequence of words or subwords or characters, depending on what level you want to process them, right? On top of these sort of sequences, we can have other kinds of structures in NLP. For instance, segmentation. That means breaking up a sequence into smaller segments that correspond to things like entities or maybe events, maybe sections of like a bigger document, speakers in a recording if you want to extract only the part spoken by one person, and so on. At maybe an even higher level, you can have this sort of inter-word dependencies, right? So this used to be a lot more popular a few years ago when I was getting started. But things like syntactic or semantic analysis, often called parsing, right? When you have this sort of relationships between words that help you disambiguate things, right? We won't get too much into this today. And alignments, which also I showed you visually here, right? Like this sort of alignments also appear in NLP. If you're, for instance, looking for, let's say, parallel text on the internet to train some sort of machine translation, you know, or if you're working with audio data and want to map, you know, a waveform that could be, you know, many measurements to like a bunch of phonemes that you know that they should be represented in there. Each phoneme will take a different amount of time. So these are just, you know, 4 kind of big types of structures that you could encounter when doing work in natural language processing. There are more, but I want to kind of do this quick tour of them so that I can hopefully convince you that structure is something that's, you know, deep at the heart of natural language processing. It's deep in how we design all the models, algorithms, or how we think about evaluation, and so on. At least at sequential level, usually beyond. Before we dive into, you know, the hairy stuff here, this is a semi-abbreviated version because we have 3 hours today. But I teach an extended version of this course at my university, University of Amsterdam. It's a course called Machine Learning for Structures, and you can find the materials on my website if you want to dive deeper into some of the things that we don't have time to cover today. In particular, if you're interested in working more with graph data, with data from biology and image data, I talk more about that in the extended course. All right, so we're going to start with a bit of a recap. And this is stuff that you've seen, I think it was 2 days ago in lecture 1. This is lecture 3, right, if you were to count the morning ones. We're going to build on the foundation that you've seen then, and possibly elsewhere too, about machine learning classifiers. Okay? So in classification in machine learning, we have to learn some sort of mapping from these inputs X to some outputs Y. And I'm using this curly set letters to denote the set of possible inputs and the set of possible outputs. And when we're doing classification, the set of possible outputs that we can assign to an input can be encoded as a bunch of labels that we can just say are 1 to up to K. We have K classes. So if you want to do K-class classification, the way we're going to formalize it is we're going to somehow obtain a feature encoder, phi, that takes inputs X and outputs some vector, you know, a vector of D numbers. And this feature encoder could be a neural net, it could be handcrafted, you know. It doesn't matter for what I'm saying next, right? So then what we do with this is we make predictions by taking the dot product between the feature vector and a weight vector for each class, right? We're gonna assign the winning class as the one with highest score between its weight vector and the feature vector. This is the sort of classification model that you've seen 2 days ago. Another way to think of this, or to maybe represent this, or also actually much more common when you implement this on a computer, is instead of thinking of K separate weight vectors, 1 for each class, we just stack all of these into a matrix, big W, uppercase W. Each of the rows here corresponds to those K weight vectors. So then this is a K by D matrix. And then we take a matrix vector product. The shapes line up nicely, right? This was K by D, and this is D by 1, right? So when we multiply the matrix by the feature vector, we obtain a vector that I call A, which is the vector of scores for each of the K classes. This is how we usually implement this, right? We put all of these weight vectors together. We do all of this sort of in a batched way. We get this. We get these scores for all the k classes at once, and then, for instance, we can do an argmax over some rows of a matrix or something like this. Okay. So you can say that the score of assigning label y to input x would be the white coordinate of this vector of scores, A. Right. To me, this is a little bit of a more natural way to organize exactly the same calculation that is written on the left. It's no different. I just kind of packed the numbers slightly differently, okay? I should also say I'm happy to be interrupted at any point if that's how we roll here. So if something's not clear, you just wave your arms, and I think somebody will come to you with a microphone, probably. So we put together a way to assign scores to each of the k possible classes. And our intuition is that we want to predict the class with the highest score, right? But we can do a little bit better, and we can give this whole thing also a probabilistic interpretation. And when we do this, we also gain, kind of for free, a learning algorithm. So when we have scores for all possible classes, what if we want to turn this into probabilities and say, we want to assign probabilities kind of, let's say, proportional to the scores. So what we would usually do with that, in order for the word proportionally to mean, we have to get rid of pesky negative and positive numbers. We need everything to be positive. So what is commonly done, you might know it under the name softmax. If we take the exp, so this is, e to the a I, something like. If we take the exponential of all of the scores, then we get only a bunch of non-negative numbers. And then we can say the probability of each possible class is proportional to the exp of the score of that class. And the proportionality constant, basically the thing we got to divide by to make sure all of these sum to 1, is just the sum of all of those scores. Right? It's just what we need to plug in here to make those sum to 1. Right? So for instance, if your classifier gives you these scores for our 4 possible classes here, we take the exp and we normalize, and we get this sort of probability distribution. Right? So this is usually called informally a softmax operation. You take a bunch of scores, you get from them a bunch of probabilities. So once we have this probabilistic interpretation, we get, like I said, for free a way to train these models, right? Which I haven't told you so far how to do. I mean, of course, you know from a couple days ago. But you can train logistic regression. That basically means you want to maximize the probability, or equivalently the log probability, of the training data. So you can maximize the sum of the log probabilities of each pair yx in your data set. So you start with a linear classification model, you give it a probabilistic interpretation, and it gives you an intuitive training objective that you can then go ahead and optimize in order to find your best weights, your best encoder, and so on. That's more or less in 5 minutes how we do linear classifiers. Or nonlinear ones is the same principle. There you also have to learn your feature encoder. Okay? And now let's throw structures into the mix. Right? At least there are at least 2 ways, two places in which you can encounter structures. In the x objects, so the inputs, or in the y objects, the outputs. Right? Note that in our presentation of the linear classifier, we didn't really make any assumptions about what is x or what is the feature encoder phi of x. Right? It can be anything. And this is key to allowing us to use structures in the inputs. We just have to design an appropriate feature encoder phi for the kind of structure that we're looking at. Yesterday you saw a bunch of these. We're gonna take the next maybe 20 to 30 minutes to recap some structured encoders like this. And then in the remainder of our class today, we're going to look at what I think maybe is the interesting and hard part, is dealing with structured outputs. Why? So predicting the structured objects in the output. That's our roadmap, let's say, okay? Structured inputs. I'm gonna start with encoding sequential data, such as text. One way to encode when your inputs are sequences, for instance, sequences of words, is a bag of words concept. This is, fairly old and like very robust, very test of time, survivor, many years. It's a simple but powerful idea. We handcraft features using this simple system for every item in your vocabulary. So an item in a vocabulary is, now we would call these kind of tokens, but that's a bit of a misnomer. We used to call them types, and we used to have a distinction between types and tokens. But I notice these days that I use the word type with my students, and they look at me very confused because people don't hear this anymore. So it doesn't actually matter because that's just terminology that linguists liked, right? But we can call them vocabulary items, and then I think we all understand what I mean, right? Our sequences, if they are sequences of words in English, they're made of distinct elements, each of them being a vocabulary item, perhaps a word, right? Now, what exactly is a word? We could argue about that sort of thing. So let's just not, and let's just say we define a list of vocabulary items. And then our sequences are made out of choices of items from that vocabulary, right? Don't get dragged down into arguments about what these things mean philosophically. So if we have a data set that contains this sort of English fragments, they're not really sentences. Like, this book is good, fairly long book, the book isn't good. One way you could build a vocabulary out of this is, this is where the messy part comes in. What do you break is, if you have exclamation mark after good, is this a single word or not? We're gonna say it's 2 words, right? So we break things up this way, and then you look at the set of unique words, items, tokens, whatever, and those are gonna be our columns. For each of these, we define a feature, phi I, and given a sequence X, phi I is going to count how many times that word, vi, appears in the sequence X. Okay, so for instance, this first column, phi 1, corresponds to the word, to the item, exclamation mark. Right? So we count that it appears 1 time in this sentence, X1, but 0 times in the others. Right? So this is a bag of words feature representation. And there are many variants of this. You can have just 0, 1, and in fact it turns out that with these 3 fragments, we end up with just 0, 1 counts, because no word appears twice in the same data point. But you can also always just say, does it appear or not? Even if it appears multiple times, you don't count, you just keep the feature at 1. All sorts of variants. It used to be the case that we would need to try all of these to find which work best for different applications. You can normalize frequencies so that it changes a bit the interpretation of these features, but all of these are generally called bag of words models. It's when your features correspond to some sort of count of whether a word appears in the sequence or not. What you should notice with this sort of bag of words models, and I think it's the reason why this name was associated to this sort of model, is that we lose word order, because essentially we are putting all our words into a bag, and then when you put things in a bag, you are not going to take them out in the same order, right? So the 2 fragments doesn't word order matter, and word order doesn't matter, will be represented in the exact same way under this sort of bag of words model, although I think most of you would agree they don't mean the same thing, right? So this is something that gets lost when your representation is perhaps too simple, right? So now we can expand this to sort of try and get some amount of structure from the sequences back into the representations so that word order maybe will matter again. If we want to integrate some sort of sequential order into a bag of words representation, again, the common and established way to do that is named n-gram feature representations. And with n-grams, we will treat n consecutive words or tokens in a sentence as a single token. So when we have something like the book isn't good, we would first transform this to a sequence with some overlaps like this. The book would be token 1. Book is would be token 2. Is and maybe would be token 3 or something like this. Right? So when we do this, we introduce a bunch of redundancy, but we also introduce some local order because now we know which two words appear next to each other. Right? And once we apply this transformation, we can go back and encode things in exactly the same way again, right? Except we're going to have many more possible unique quote-unquote words, which now become bigrams, right? And you can go even further. You can make unigrams, bigrams, trigrams representation separately and concatenate the matrices, and you end up with many, many features that could capture various degrees of local sequential structure in your inputs, right? So you could do this, but it comes at a cost. I leave this as an exercise to you if you want to practice counting how many n-grams are theoretically possible to be observed if you have a vocabulary of size V words, single words, let's say. But also if you have a given data set, how many n-grams can actually appear in that data set. Usually it's going to be much less than the theoretically possible ones. If this is something new to you, and if you find it interesting, I leave it as an exercise to think about it at home. A twist, I guess we could call it a modern twist, on the bag of words idea, comes from using embeddings. So the bag of words idea stayed popular for a long time because it allowed us to have successful and powerful linear models. But once we started training with success all kinds of deep models, nonlinear models, these ideas have morphed into something a little different. And that something is embeddings, word embeddings, token embeddings. And this in general applies beyond NLP as well, anywhere you have data made up of discrete tokens, discrete choices that can be plugged into various parts of your object. I think so. This also holds then for DNA and so on, but we don't go too deep into that here. If your input sequence is represented as something discrete like this, so you can encode it as a sequence of integer, let's say, identifiers. And with language data, we can do this. We first build our vocabulary and we assign to each word a number from 1 up to vocab size. So once we can encode our sequential data like this into this integer representation, we can map the sequence to a sequence of embeddings by mapping each word, let's say, to an embedding. So what's an embedding? It's a d-dimensional vector that corresponds to that particular word. And in general, these are just like stored as it is. Right? So if you think of this feature E of I, sorry, not feature, it's a function that retrieves a row from maybe an embedding matrix that we learn, and it returns this vector. Right? These embeddings can sometimes be fixed, maybe extracted from somewhere else, or just be part of the trainable parameters of your model. Right? And if you have a sequence of length L, if you apply this embedding mapping to each position, you get a matrix of size L by D. So once we have a feature, an embedding representation of our sequence, we can do what is sometimes called continuous bag of words. We can pool these embeddings together. Pooling is an important word that we're going to see again. We get by averaging out, for instance, or maybe taking the max coordinate-wise of our embedding vectors to get a single vector. So this was a vector of size L, and importantly and annoyingly, L will be different for every input. We map it into L by D. D is the same for every input. It's a fixed choice we make. And then when we average those vectors together, we get a vector of size D, no matter how long the input sequence was. So this is a way to kind of use embeddings representation to flatten sequences of various lengths into a fixed size dimension. So we call this pooling. And when we apply pooling directly on top of embeddings, we get what is known as continuous bag of words. Okay? Just like in standard bag of words, here word order doesn't matter because the pooling strategy doesn't care in what order we add these in. Okay. So this still lead to quite powerful models. They work quite well. We're going to build a little bit on top of the pooling idea and talk about convolutionals for encoding sequential data. I'm going to move through this a little bit quicker, but I do think convolutions weren't covered yesterday, I'm not entirely sure. So I just want to show you how this method could be applied and how it relates to pooling. Let's say we have a sequence of word embeddings. So we've already applied our embedding stage, and now we're drawing these things bottom up. So this is E of x1, E of x2. So here at the bottom we have a bunch of embeddings, and we want to apply some sort of filter to recognize patterns in this sequence. Right? Now what is drawn here in this deeper red color is called a filter. So a filter has length k. This is sometimes called the window size or the filter size. And its dimension matches the dimension of the embeddings. Right? So we get something that can be, let's say, overlaid to a part of the input of size k. Okay? Usually you would define this first in the single channel case where these are just vectors and not embeddings, but we are skipping a little bit over that part because we don't have a lot of time for this. So a filter is a D by K matrix. This is D and this is K, and our input is D by L. So K is less than L and K is fixed, but L can vary, right? So we can slide this filter around. Okay, so when we apply this filter here, what we essentially do is we take the product of this with this, this with this, this with this. You know, we just put them on top of each other and multiply all numbers together and add everything up. We get a single number. This is known as an inner product. You can do inner products on matrices as well. It looks like this. And when you do this inner product between these two objects, you get a single number which you can plug in into the position corresponding to where the center of your filter was. Okay? But now as you slide this filter, including here and here, you're going to get a different number. Right? So when you apply a filter along a sequence, you're going to get another sequence of the same length, but now the sequence contains just one number, right? So the output is one number per window location. And we're not going to go into details, but you know, you have to do some paddings and tricks and stuff to handle when you're exactly at the edge. Just imagine everything else is zeros forever, right? Now, if you do exactly this, but not with one single filter, but with m different filters, let's say imagine one behind the other, when you apply each of them, you get one number. Then if you stack those numbers together, you get M outputs. So we started with L by D. We applied M filters by sliding them along in parallel, and then we end up with M by L. You can take M equal to D, for instance, and then you can repeat this sort of operation. You can stack a bunch of these convolutions together. So this is a one-dimensional convolution, a sequential convolution. And this is actually a pretty cool and pretty powerful model to use for representing text data. Why? Because you can sort of see this as a continuous version of n-grams, right? So if here we have, if these embeddings corresponded to something like the film was good, but something like this, then you can have this filter as being maybe a detector for a pattern of the form film was good. But because everything's continuous, it could also detect something like movie was good. It could activate with a high value when it matches that sort of pattern, with a low value when it matches anything else. And then it can think of it as a sort of more soft, more flexible sort of n-gram representation. Okay? These are convolutions for sequential data. The next model that I think you've covered a little bit, I'll just do a quick reminder of, is the recurrent neural network model, which at its heart, if you kind of look at it as a black box, it's the same as a sequential convolution in that the input is, where did I have this? L by D, and the output is something like L by M. It takes a sequence of vectors, it outputs a sequence of vectors. You can think of it as just like this sort of signature, but the way it works internally is very different. So whereas the convolutional model from before applies kind of a bunch of calculation in parallel locally, the RNN actually processes the sequence in order with like full dependence between every step and everything that came before. So if you remember recursions from like programming, essentially we can define each time step, we can define a representation zt at position t as some sort of function of the input at that position, and this is the recursive part. It's the previous representation, but this is not defined, so you can plug this back in, and then you get a composition of a function applied to itself, which means eventually everything bottoms out with this z0, which is fixed. It's perhaps a parameter that you learned. But then zl, the last one, will depend on everything that came before, right? And the final state then has seen the entire sequence. It's kind of aware of everything also that was in the input, right? It's part of its equation at least. Right? Then the question is, can the parameters kind of make meaningful use of that? So the simplest RNN can be defined in like a quarter of a slide here. We take a linear function of the input at position t, a linear function of the previous state, some sort of bias vector. We apply some nonlinearity, and that's it. If you apply this equation recursively, you get, in a couple lines of code, a encoder that can take a sequence, output a sequence, right? And everything is accounted for. Will it work? Great. Well, it remains to be seen, but this is the core of the idea. Spoiler, it's not in my slides because I want to rush through this a little bit, but it doesn't work so great. But there are variations of this model that introduce gates, and those variations worked very well, and they drove neural net NLP for maybe like 5 years before transformers came along. That was known as the LSTM neural net. Let's go back to the pooling idea that we talked about earlier. So pooling, we saw it when I showed you a continuous bag of words. The idea of pooling was that we could have a bunch of vectors of the same size, but we want to kind of compress all of these into a single fixed size representation. So we could use something like average pooling, which is just taking the average of those vectors, okay? In general, the idea is to combine n input vectors into one. You could also use max pooling or other things, but by default, you want to combine them in a way where each vector has equal contributions, because otherwise, if you're picking favorites, you need to kind of define why one vector would be your favorite over another. So pooling standard without any kind of a priori information that one vector is more important than another should be equal contribution, right? But what if you know or you assume that some of the inputs should matter more than the others? What if we believe that for the task we're trying to model, maybe most of the words in a sentence don't matter? Right? So then we could try to build some sort of weighted average pooling. Instead of weighing everything exactly the same, maybe we want to assign different weights alpha. So as long as these weights alpha sum to 1 and are non-negative, then this is still an average, but it's an average that can be pooled towards some of the inputs, right? If all weights are 0.2 in this case, for a sequence of length L, if all weights are 1 over L, then we just get the uniform average, right? But then if you set one of the weights to something like 0.95 and then fill in the others with whatever is needed to sum to 1, then you could get a weighted pooled vector that mostly comes from only one of those vectors and not from the others. So this alpha weight can let you control the relative importance of some of the inputs, right? But how to choose these weights? How do we know which of the words are important in a given context? This is essentially the idea of an attention mechanism. An attention mechanism is kind of a smaller classifier inside of a neural network layer, if you want. And it's a classifier that kind of tries to predict which word is important, right? That's at least one way to think about it, right? If you have a representation of the context as a vector Q, this can tell you more or less what are we looking for in a word. So we define which word is more important. Then you can say a word is more important if its dot product, let's say Q times Zi, is greater than Q times Zj for the other J's, right? So we can think of this as if we're trying to classify with each word being like a class. So that suggests that we can apply something like softmax to get those weights, right? So we're gonna assign a higher weight to the words that have a higher dot product with this context representation, this query vector that learns to select what word is more important right now, right? And of course, it could activate high for 2 or 3 more words. It doesn't need to be just one, right? But the shape of this kind of looks like a classifier. Except, instead of doing classification with it, what we do is we do weighted average pooling, right? So that's an attention mechanism, right? Given a query, so the context vector Q, and given n vectors z1 up to zn, we first compute the alpha weights this way, and we then take a weighted average of the z's with those weights. The idea being to infer which words are important and then to average them proportional to that inferred importance, right? You can think of that importance being how geometrically aligned they are with the context vector Q, okay? Now, in different applications and different kind of models, you can use this idea of attention with the context being perhaps just a static learned parameter. For instance, if you are doing sentiment classification on sentences, Q could be a vector that just learns to align with very high sentiment words, positive sentiment words or something. And that's just it, right? It will select for those words. If you're training, for instance, on multiple tasks or domains, data that comes from different sources, but you want to train a single model for all of them, Q could be a representation of the domain, right? So one Q could be which words are positive sentiment when looking at movies, but another one could be what words are positive sentiment when looking at electronic reviews, something like this, right? Like reviews of home appliances, right? In machine translation, we usually take ZI to be the English words, and then the queries. Now there's something missing from my slide, but the query comes from an encoder in this case. That's a more complex model that we would need more time to fully cover. So attention is this sort of very general mechanism that allows us to pull together some vectors in a dynamic way that gives preference to some vectors over others. Essentially, and without going too much into details, the very popular transformer architecture today is many, many attention mechanisms put next to each other and then put on top of each other, right? And you can see that this combines strengths of both convolution models and the recurrent models that we've seen before. Like an RNN, it's global because every output can, in theory, depend on every possible input, which is not true with convolutions. There, everything was local in a window, right? On the other hand, it's parallelizable like convolutions because each of these can be calculated without bothering with the others next to it, right? And to make it sequence aware, we have to add something called positional embeddings to each of the vectors. And that's a weird, interesting technical trick in the transformer that will come back in a few seconds. I'm not going too much into these details. I think you are fairly familiar with the transformer model already. So this was a recap. I more or less assumed that you have at some point seen this sort of sequence representations. What they all have in common is they take a sequential input, they give you a sequence of vectors in the output. And whereas the input vectors are, usually we would call them static embeddings, right? They just tell you what word is there, but they don't tell you anything else about the rest of the sequence. After you applied your encoder, you get another sequence of vectors, but now they are aware of a lot more, right? And this is where the structure comes into play, right? The output vectors have been informed by the sequential nature of the input, okay? So convolutions, recurrent networks, and transformers, they all fit this sort of shape. L by D input, L by M output, M could be equal to D or not, taking sequence into account, okay? I want to take not long, but just a little bit to give you also a bit of a view of the world of graph data and encoding graph data. This is usually mostly done by people working with things like proteins or molecules, but also things like social networks, transport networks, and things like this. But I think it's also very interesting for people working on natural language processing. I'll tell you in a moment why. So a graph mathematically is defined like this. You got a set of nodes, which we usually just label 1 up to n, right? And we have a bunch of edges between them. This could be directed or not. A directed edge means that we can have an edge from u to v without also having an edge from v to u. Undirected means if one of these exists, the other also exists. So this can be encoded as an adjacency matrix of size n by n when the element AUV is 1, if and only if there is an edge between u and v, okay? Now, for instance, in molecules, or also like if we have some sort of richer object that's being represented as a graph, every node can also have a type, like carbon, hydrogen atom, and so on. But we can assume that all edges are of the same type. There are two kinds of machine learning problems where the data comes in as graphs. The first type of problem is when every data point, xi, with its output yi, so each of these xi's is itself a graph, a different graph. So our data set is a set of distinct graphs, right? examples of this sort of problems are if our data set is a data set of distinct molecules, and for each molecule you want to predict some property like solubility. Or if our data points are, let's say, computer programs written in code, right? But rich representations of codes could include graph, like abstract syntax tree representations or things like this. And you want to predict whether that code is malicious or not, right? In NLP, this sort of problems where each input point is a graph can be if you're doing various kind of classification tasks on text that has received linguistic annotation, either automatic or manually. For instance, you have already done some form of, I don't know, coreference resolution or parsing or analysis that gives you some sort of graph structure between the parts of the input, right? So this used to be a fairly popular approach to build pipelines, where you first enrich your language data with a lot of this sort of additional annotation. And then your models can be more powerful because they know when two similar references maybe refer to the same thing or not. More recently, there's a lot of work in generating natural language text from structured objects. So this includes from so-called AMR, abstract meaning representation, is when you can have a system that generates something that it wants to say in a very formalized language, and then you want to convert that language into like fluent English language, perhaps, right? Or if you have input represented as a knowledge graph, maybe extracted from Wikipedia or something like this, and you want to generate answers or something informed by that, then your inputs could be different graphs, different subsets of a knowledge graph for each point, right? So in this sort of problem, the input can be given as a sequence of node labels and an adjacency matrix for each of them, AI. Okay? But the other kind of problem that you may encounter is when, in a sense, your whole problem, your whole data set is one big graph, right? And it's quite different from the first one. And this usually appears in problems that take the link prediction form. Think about, for instance, follow suggestions on social media, community detection, classifying bots on different platforms. You have a big graph with interactions between them, but you want to make predictions at node level or maybe at edge level. In NLP, these sort of problems are known as like entity linking in graphs or knowledge-based completion or things like this, is when you have some sort of information in a structured representation of knowledge, but not completely so, and you want to fill in some of the things you don't know. When dealing with one big graph, it's a bit harder to set up experiments to evaluate correctly because learning is more complicated. So these are some applications of graph data that you may encounter in natural language processing as well. And I will show you briefly a model that can encode graph inputs in a way that can actually let us work with both of these kinds of problems. This is known as a graph neural network. Right. So just like for sequence encoders, we would have a sequence of input vectors x1, xn, and we would generate a sequence of outputs z1, zn. With graph neural networks, we're going to do the same thing, but instead of assuming that the vectors are, let's say, linked sequentially, we're going to use the graph structure that is given by the adjacency matrix A. Okay. So the way the graph neural network model works is an iterative process. At the first iteration, let's say the initial iteration 0, we just give each node its input static embedding that corresponds to, let's say, what word is there. Very much like for sequential models. But then at each iteration, the embedding of a node gets updated as a function only of its neighbors, right? Only of the embeddings of its neighbors at the previous iteration. So this node that is highlighted receives an update from, this is sometimes called like a blanket, right? Like it's a set of its neighbors. Okay? So you can think, for instance, as this is a form of message passing along the edges. You form a message from the neighbors of that node, and then you apply an update to the representation of that node in a way that could be perhaps quite similar to the RNN. So in this case, we have, let's say, a linear function of the word itself's previous representation plus a linear function of the message from the neighbors with some sort of bias term, and we apply a nonlinearity, and that's all we need to pass one round of messages. Now, if you pass a single round of messages, every node just gets informed by its neighbors. But if you pass several rounds, then eventually you will end up with information being propagated from all the way in the graph to every other node. Okay? Now, as we've just defined it, a graph neural network will give us these embeddings of every single node. If you want a single embedding for the whole graph, you can again turn to the idea of pooling, right? So you might want to average representations of all the nodes and treat that as a representation of a graph using average pooling, or you can do some form of max pooling. Both of these are done in practice. Now, one thing we want in a graph encoder is known as permutation equivariance. This means the structure of a graph doesn't change at all if we relabel, if we permute the labels of the nodes. So if we take node I and node j and just replace them with one another while also keeping all the links correctly, all the edges correctly, then the graph didn't change. It's just renamed, right? So we want the output of a GNN to also respect this. Well, this can be encoded mathematically too. If we store the node representations as a matrix X with an embedding for each node, and the adjacency matrix is then something like n by n, right? Then given any permutation matrix, a permutation matrix is a matrix with exactly 1 0 in each row, 0 everywhere, except for a single 1 per row, a single 1 per column. When you multiply by this sort of permutation matrices, you are permuting the elements in your vector that you're multiplying this. If you permute, sorry, that was my wake-up alarm. If you permute these rows, so essentially the node representations, and if you also permute the links in the same way, both the rows and the columns of the adjacency matrix, then the output of the graph encoder should not change at all. It should be exactly the same, but permuted by p, of course, again. So this is known as permutation equivariance. If we swap the nodes in a graph, the representations should change in the same way, the exact same swaps, okay? So there are a bunch of variants of the graph neural network that you can find. If we notice the resemblance with the RNN, then we can think of adding gated variants like some sort of graph LSTM where the update for each node is gated. This is beyond the scope of our lecture. We can also have separate weight matrices for each iteration. And you can support different types of edges as well in a graph by changing the weight matrix that you multiply in, essentially. And you can also do various forms of normalization over the neighbors. Instead of summing the messages, you can average them or something like that. All right. Finally, I want to tell you why I was insisting on the transformer and its node, and its, what are they called? Positional embeddings earlier. Self-attention, and by extension also the whole transformer encoder, with the exception of the positional embeddings that we add into the inputs, right, turn out to be permutation equivariant. Because I told you an attention mechanism is a way to apply a query to do a sort of preferential average of a bunch of vectors. Now, if you swap the order of those vectors, nothing changes because we still use the same query to look things up. So just like in the graph neural networks, the messages were computed as a sum, you can also use self-attention over the neighbors with some query, and in fact, you can just use self-attention as a graph encoder. Right? If you swap the order of any of those inputs, the output just changes in the exact same way. So it's permutation equivariant. Right? You can use transformers just like they are used for NLP, just without the positional embeddings, and then they become permutation equivariant. In other words, the word order would not matter anymore, but that's what we want for graphs. The difference is instead of allowing attention to go to any possible word, you should constrain it to only go to the neighbors in the graph. So like we should not have this edge, for instance. Okay. So this is how you could apply transformers with masked attention patterns to graph representation. All right, that was a quick tour through the world of encoding sequential inputs and also briefly encoding graph data. All right. We can next move on and start to talk about predicting structured outputs. Of course, most of this will be in the second half, but we have about 30 minutes now to get started and at least set up the problems that we're gonna dive deeper into in the second half. As a reminder, this is the scenario we were in so far. The inputs were structured, and we just bothered with designing feature representations, and this could be plugged into familiar unstructured outputs like classification, regression, or whatever. But what we're going to do in the next part is focus particularly on structured output objects. So the kind of structures or sequences that we saw in inputs, now they're going to be what we are trying to predict. Okay? In our definition, in our world, structured outputs are discrete objects that are made out of smaller parts, and those smaller parts interact with one another. And that's what makes prediction hard, is because they interact and they constrain each other. The presence of a part in the output somewhere could interfere with what you're gonna be able to predict in other parts of the output. So you cannot do these completely independently. Consider a quintessential structure prediction problem, which is the assignment problem. Let's say you have 4 jockeys and 4 horses with some sort of pairwise preferences between them. How many possible ways are there to assign 4 jockeys to 4 horses, 1 each? The answer is 4 factorial. This is number of permutations of length 4. So this is 4 times 3 times 2 times 1. So in this case, this is just 24, you know. But if we move to much higher numbers of jockeys and horses, quickly the number of possible assignments grows very quickly. And you can probably see that we cannot simplify this problem by making each assignment separately. You know, we have to consider all assignments together because we cannot give the same horse to 2 different people, you know, accidentally, right? And if we just go by preference, that might happen, right? So we have to consider the whole structure globally. So the size of the output space in this case is n factorial, and this grows quite fast with n. In fact, this is what you're gonna see with structured prediction in general. the space of possible outputs grows very, very fast. Remember what we said, what was it like? About an hour ago, that to train a classifier, when you have a score assigned to each class, if we use a probabilistic interpretation, this is known as logistic regression. And it kind of gives us for free a way to train a model. This is known as the logistic regression loss. And the loss would be the negative log probability of that class, right? Well, why is because, why negative? Because we're minimizing a loss. We're maximizing the probability, right? So with the definition of the softmax, the logistic regression loss takes the following form. We want to minimize the negative score of the correct class, and we want to minimize the log sum x of all of the scores, right? If you think about what this ends up doing is minimizing a negative means increasing. So you want to increase the score of the correct class, and we want to decrease the score of every other class, right? But this score is passed through this log sum x, which is a soft maximum. And perhaps you also remember the perceptron loss, which is very similar, but instead of a soft maximum, you have a hard maximum over all the scores. I just want to mention it because it's also useful when we move to the structured case. So this is, these are the computations that we need to be able to do in order to train models with this sort of probabilistic objective. For classification, how did this actually look like when you try to implement this from scratch? Your space of possible outputs is 1 to ... up to k. And you have a linear or neural net model or something that predicts a vector A of scores for each class, right? So then you say score of y is AY, is the white component of that vector. So then how do we compute this loss? This is just a lookup at position y. And this, you take the x of the whole vector, you sum the whole vector, you take the log of the result. So this is how you would implement this from scratch, right? But now, in the structured case, for instance, for the horse jockey problem, remember that the set curly y becomes very, very large. So what happens? We might be able to compute the score of the given true assignment, but this would be essentially a sum over every possible assignment of n horses to n jockeys. So this sort of thing is where predicting structured outputs gets tricky. We will have to, in some way, do this sort of aggregation over a really, really large set. Okay? And that's the tricky part. So here's what that would look like for n equals 4. For n equals 4, it's doable because there are only 24 possible assignments. So these are the assignments. If we have a scorer that can assign a score to every assignment, for instance, let's say the scorer looks at the preference of the jockey, the preference of the horse, combines them together somehow and gives you a number, right? Then we would be able to compute a total score for every assignment. And if we apply softmax to all of these scores, we would get a distribution over structures, a distribution over assignments, right? So that's the generalization of classification to the structured case. We're predicting a distribution over all possible configurations of this structure, right? So in this case, there are 24 such ones, and I can show you the full distribution on the screen. But more generally, this cannot be done, right? For big N, we cannot plot this, we cannot enumerate this, we cannot write a for loop that looks over all of these and just sums something, because it becomes very, very slow very quickly. So that's where things get tricky. We have to figure out how to compute the following things. How to score a configuration, right? This is, relatively speaking, the easy part. Once we design the scorer, we need to also be able that we can do the following. We can predict. So we want to be able to answer the question, what is the highest scoring configuration? And this involves an argmax over the entire set Y. And for learning, for probabilistic learning at least, we have to be able to compute this log sum exp over, again, the entire set of possible configurations, curly Y, right? So we have to be able to somehow solve these two problems. And the challenges are, well, on one side, that the set Y varies from point to point. We saw it's n factorial, but n may be different for different stables, I guess. And more importantly, the size of Y can get very, very large. So we cannot anymore just solve this with a for loop over the length of the vector, over all scores. We have to do better. It turns out that, well, there are, in fact, I'm being optimistic on this slide. For certain structures and certain scoring functions that we're going to deal with today, we have efficient algorithms that can do all of this stuff. I'm going to show you those algorithms. There are also many structures for which there are no efficient algorithms, so we have to turn to all kinds of approximations. And there's also something in between. There are some structured problems for which the algorithms I will show you today don't work, but there are some specific other ways to learn with them exactly. Right? In my full class, if you want the full story, I cover all three of these cases. But with our limited time today, I will only show you dynamic programming. I'll show you a class of problems, a class of structured prediction problems that can be solved with the same family of algorithms. If we can represent the problem in a certain form, then we will be able to do maximization, computing probabilities, and we'll also be able to do sampling with the same sort of shape of algorithm. So I think this is fairly powerful, and it applies, like I said, not always, but to many problems of interest. I will show you two applications. One of them in sequence tagging, which we'll also do in the lab, and one of them for sequence segmentation. And finally, we will close with talking about evaluation. So the computations that we need to be able to do, once again, are to score a structure, to find the maximum scoring structure, and to do this log sum exp over all possible structures. Let's talk about graphs again. We briefly talked about graphs when I was showing you how to encode them. But now we're going to use graphs in our algorithm. So we need to think of them a little bit differently. First of all, we're going to define the weighted directed graph. This is a little bit of a richer object than before. We still have nodes and edges. The edges are directed, and in addition, every edge has a weight associated to it, W. You can think of the weight as a function from the set of edges to the set of real numbers, but more visually, what this function does is on each edge it writes a number, right? That is the weight, or if you want, like the reward associated with traversing that edge. Okay? A path in a graph is a sequence of edges. And all of those edges must be 2 by 2 linked. When one edge ends, the next one must start. Okay? We can extend the weight from edges to paths by summing up the weights of each edge along the path. So if you have this sort of path s to t to x, that the weight of the path, sttx, is going to be 6 plus 5, in this case, 11. Okay? And we can concatenate two paths whenever this is legal. So when the first path ends and the second path starts, if that node is the same, then we can concatenate those two paths to get a longer path. There is one special kind of path called a cycle, and that is a path where the last edge points to the same node where the first edge started from. So it's a path that closes back on itself right at the end. Okay? Graphs, so directed graphs that don't have any cycles are called directed acyclic graphs, or DAG. So a DAG is a directed graph in which there are no cycles. This is an example. You're going to see that no matter how hard you try, you cannot find in this graph a path that closes back on itself. Okay? These graphs are a little bit special because we will be able to do some things in them more efficiently than the general kinds of graphs. Another concept I want to introduce is the concept of the topological ordering of a graph. If you have a directed graph with nodes v and edges e, a topological ordering of this graph is an ordering of its nodes, so an enumeration of the nodes in a certain order. We label them 1, 2, up to n in a certain order, such that if there is an edge from any vi to vj, then the number that we assign to I has to be less than number j, right? So this means in the topological ordering, there are no arcs that go backward, that go against the topological ordering, right? Not all graphs admit a topological ordering. And in fact, it turns out that this is equivalent to whether a graph is a DAG or not. Assigning a topological ordering to G and verifying that this ordering is indeed correct would imply that that graph is a DAG, because otherwise we would have a backward edge, and that would have to form a cycle. Okay? So this also works backwards. If we have a DAG, then we can label its nodes in such a way that no edges go from a higher label node to a lower label node. Armed with this, we can start looking at the set of all possible paths in a DAG. So given a DAG, and given a topological ordering of the nodes in this DAG, so we just assume that the numbers 1 up to n correspond to this topological ordering. And this is true for the graph here in the picture. Notice there is no edge from a higher number to a lower number. Consider the set curly y subscript I. And I'm picking this letter intentionally here. It's going to relate to what we have been calling y so far. But for now, think of yi as the set of paths that start at the first node, at node 1, and end at node I. If we can formulate a structure prediction problem in the case where the space of structures that we are trying to optimize over is the set of paths yn. So in this case, from 1 to 5, right? We are going to develop algorithms to compute the score, the argmax, and the log sum exp. Suspend for a moment the question of how do we relate these paths in this graph with the structures that we're trying to predict. I will show you that after we develop the algorithms. Let's assume that that construction exists. We have a way to represent our structures as paths from 1 to n in this sort of DAG. How do we compute the score of a path? So if we have weights on each edge, then we can say that the score of a path is the weight of the path. So the sum of the weights of the edges along the path. So scoring is easy. We just, given a path, we add up the edges weights along that path. How do we find argmax? How do we find the maximum weight path? The path from 1 to 5, or in general from 1 to n, whose total sum of weights is the best, is the highest. Now, if you took some sort of graph algorithms or data structures and algorithms class, you would know that this is not an easy problem, right? You cannot solve it naively with, let's say, a greedy algorithm. So if you just start at one and you try to follow the best paths forward that you can take. In this case, you could take this path, for instance, then you'd have to take this path, and then you take this path, and you would end up with a score of 25, right? But you'll see we got misled, because if we took the less appealing decision here at the first step, we could get a score of 30. So we cannot make decisions locally quite like that, greedily. On the other hand, there are efficient algorithms that can find optimal paths in graphs in general. So one such algorithm is Dijkstra's algorithm, which is a standard one that you probably saw in school at some point. So this works for a more general class of graphs than DAGs, graphs with no negative cycles. However, DAGs are a more restricting structure. And in DAGs, there is a more efficient algorithm for finding the maximum weight path. So let's find this algorithm together. Okay? Our goal is to find a max weight path from 1 all the way to n. We're going to first replace this problem with a slightly simpler problem of finding the maximum weight path from 1 to I for some node I between 1 and n, right? So we're going to build up the solution incrementally based on this. So we want to find, also for simplicity, we're not talking about the path itself, but let's talk about what is the weight of the path, the weight of the path with maximum weight from 1 to I. We want to compute this, okay? In any graph, the following insight holds and helps us. Any path from 1 to I is an extension of some other path from 1 to j concatenated with the arc ji. Right? This is just a way to think about a path. Right? So from any path, you can remove the last edge and then think of it as being a slightly shorter path extended by one arc. This is just peeling off one edge off of the path, right? So you could write this mathematically like this. If y is a path from 1 to I, then we could write y as y prime concatenated with ji for some j in the set of predecessors of I. This is the graph notation that I forgot to introduce. It means the set of nodes that have an edge from them to I. And some y prime. Let's also draw a concrete example. So this path 1, 3, 4, 5 can be seen as the path 1, 3, 4 concatenated with this last arc for 5. That's all I'm saying, like that you can peel off the last arc of a non-empty path, and you will get a slightly shorter path plus 1 arc. Just from this, we can write the following recursive expression of the max weight. For any I greater than 1, the best path from 1 to I is the best among the extensions of the best path to the predecessors. So, Mj is the best path, is the weight of the best path from 1 to j. Mi is the weight of the best path from 1 to I. But because j is a predecessor of y, that means that Mi has to be the best among this set of choices. So in other words, what I'm saying is, the best path from 1 to 5 can be only one of 3 things. Either the best path from 1 to 2, let me change colors here, extended with this arc, the best path from 1 to 4, extended with this arc, or the best path from, no wait, 3 is not a predecessor. So it's actually just one of these 2 possible choices, right? Now this graph is very small, but imagine that in here, in between, you could have many, many more nodes, an arbitrarily complex DAG. But the best path that ends in 5 has to pass through either 2 or 4, no matter how many more complicated things you have before that. So this allows us to kind of find a relationship between the problem we want to solve and the slightly smaller problem in this case, right? So this allows us to express the solutions recursively this way. So far, both of these things just work in any graph. We can write also a proof if this makes you happier. It does make me happier. By definition, Mi was the maximum weight of a path from 1 to I. So we could write this using insight 1 as the maximum over paths 1j to some predecessor of I, and the maximum over yi itself. So if we rearrange these terms in the parentheses, we will recognize that this is just again the definition, but now applied to Mj. And that's the proof. It's just rearranging terms a little bit and applying insight 1. This just by itself doesn't get us anywhere yet, because this holds for any graph. And if you just try to start from the end and go backwards and so on, in general, you could end up chasing your tail and ending back, in a worse place than you started from, if you are in a general graph. But if you're in a DAG, there is one more insight that turns this observation into an actually super efficient algorithm. In a topologically ordered DAG, if you have a path that goes from 1 to I, the nodes in this path can only be less than I. Otherwise, we would have hit a cycle, right? So what does this mean? It means that these partial solutions, Mi, Mj here, you can compute them incrementally. You can start by computing M1. M1 is the shortest path from, the highest weight path from 1 to 1. This is the empty path, always, right? We can compute M2. It's the path with a single edge, because we only have one possible way to go from 1 to 2. The same for M3. And then when you have to compute M4, now we finally have a choice between 1, 2 and 2, 4, or 1, 3 and 3, 4. But because we only need to pick one, right, we can compute all of these maximum weights incrementally, following along the graph in topological order. So combining insight 2 and insight 1, we essentially get an algorithm. And this is known as the Viterbi algorithm. Given a DAG arranged already in topological order, we want to output the weights of the maximum path M1, M2, up to Mn. So these are the weight of the maximum path up to 1, the weight of the maximum path up to I, and so on. Like I said, M1 is always 0. It's the empty path from 1 to 1. M2 can be considered by extending that empty path with exactly one arc, right? The arc 1, 2. It's only one choice, right? But in general, you can apply the recurrence. So we apply this proposition. You can even forget about any intuitions if you want. Think of this as a mathematical expression, right? That depends on mj. And insight 2 tells us that the only j's that you might need to compute that maximum are less than I. So that means if you iterate over I in order from 2 to n, you will have all you need to compute this as a maximum over essentially a small number of things. This is at most the size of edges that go into a node. Okay? So this is the core of structured prediction with dynamic programming, essentially, is that you can find the maximum weight path by extending these paths with one arc one at a time. Okay? There is one more insight that we need to recover also the optimal path itself and not just its weight. And that is our insight 3. There could be ties, but a path that achieves the maximum weight mi, so I should say this is weight mi, is made out of the edges j star I, where I'm using j star to mean the node selected in each of these maxes at each iteration. Okay, so we can reconstruct the maximum path after we finished our forward pass through the DAG from 1 to n by going then backwards and following the maximal weights, at the maximal weight edges by following from I to j star and then to the corresponding j star that preceded it and so on. So we have to unfold things then from back to start. So this is often called a backward pass of the Viterbi algorithm. So we start with an empty path. We add the edge between I and the predecessor of I. So we concatenate like this. And then we repeat until we reach the start. The complexity of this algorithm scales with the number of nodes and the number of edges. So we kind of took a little bit of a dive away from NLP world and we're just talking about some algorithms. I promise you, be patient, and in maybe 15 minutes we will connect it back to reality, right? My goal for the next maybe 5 minutes is going to be to convince you that these insights and this algorithm that we just derived together indeed correctly lets us find the path of maximum weight from 1 to n in a directed acyclic graph in a DAG. Okay. Once again, how did we come up with this algorithm? So we are searching for this maximum weight path in a DAG from 1 to n, and we made first the observation that the weight of the maximum path from 1 to I must be the best among a handful of choices for all predecessors of I. So for all nodes j that have a direct edge from j to I, for all of these, we consider the max among the best path to that j plus the weight of a single next arc. So this is an observation that holds in any graph, but then on top of this, we observed that in a directed acyclic graph, if we process the nodes in topological order, we always have these mi's already computed for us, because to compute mj, the other way around, to compute mi, you only need m1 up to mi to have them already. So then the third insight was that we can also reconstruct the path backwards. That's a bit harder to see without an example. And also, as a small reminder, I told you earlier that greedy doesn't work. So if you just start from 1 and greedily pick the max weight outgoing arc every time and try to traverse this way, we've seen you're not going to find an optimal solution because it would mislead you. You're going to do this, and you're going to end up with a cost of, in this case, 25, but here we can do better, right? We can get 30 by going this way. Okay? So now we're going to see that in this graph, the algorithm that we have called Viterbi will indeed help us find the right path here. So let's go through this step by step. It shouldn't take long. So we're going to eventually fill in this table. This is M, and we're also going to have a table of predecessors pi. So we're going to initialize M1. So what is the maximum weight of a path from node 1 to node 1? We're just going to call this 0 because it's an empty path. Okay? And this predecessor here, we can just leave it empty. I'm going to write, if it's Python, we can say none, you know, something like this. There is no predecessor of the starting node. There is nowhere that we came from. We just started there. Okay. Then the algorithm goes like this. For I equals to 2, we must consider all of the paths from a predecessor of 2 into 2 and pick the best among them. But there is only one possible predecessor of 2. And that is 1. So we really have only a max over a single thing. But I'm going to write it down anyway. So we have, excuse me, M2 will be max over the following choices. J equals to 1. That's the only predecessor. So then we have M1 plus W of 1, 2. If we plug in the values here, this is 0 plus 10. We have a maximum over a single choice. So, you know, it's not a lot of work to decide that the value that we get here is 10. Right? And in the predecessors pi, we're going to put down the argmax. So the j, the index of the node that we selected in that step. Okay. So here we're going to write 1. And this was our first step in the algorithm. It was these two. At the next step, M3, what's going to happen in M3? I'm not going to take up the space on the slide because the exact same thing happens. M3 has only one predecessor in the graph. You can only get to 3 if you come on the edge 1, 3. So everything looks exactly the same. except now the weight of that arc is 15 plus 0, and the predecessor is still 1. So I'm not going to take up space with M3. M4 gets more interesting, right? I forgot how to write. M4 is a max over 2 choices this time, because the node 4 has 2 possible predecessors. You can come to it from 2 or from 3. So if we come to it from 2, then we have to consider here M2 plus W24, the maximum weight up to the predecessor, so up to 2, plus the weight of a single arc, 24. But you see, we already calculated M2 because the graph is a DAG and we are processing things in order. So we know that M2 is 10. We look it up here, right? And the weight of 24 is minus 5. So adding these together gives 5. What's the other option? J equals 3. M3 plus W34. Well, M3 was 15. W34 is 0. So the answer here is 15. So what do we fill in? Which one wins? The second one wins. So here we write 15 again. And what do we write in the predecessors? 3. That's where we came from. And then we have to handle M5. So once again, we have a max between 2 different choices now. And what are the predecessors of 5? We have 2 cases. Oh, and also here, what I'm going to do is I'm going to delete the edge we didn't take, right? So for M5, we have 2 possible choices. Either J equals 2, where we have M2 plus W25. What is this? M2 is still 10. W25 is now 20. So this choice has a reward of 30. The other choice is J equals 4. M4 plus W45. What is M4? We just calculated it. It's 15 plus 10. 25. Which one wins? You see, the correct one wins. So the branch J equals 2 with a total reward here of 30 is the one that wins. So then here we fill in 30. And for pi 5, we fill in that we came from 2. So we keep track of the best reward that we've accumulated so far and of the branch we took to get there. We need to keep track of both of those things. Only one is not enough. So now we filled both tables, and if all you care about is what is the weight of the maximum weight path, we're done. That is here, it's 30. But if you also want to know what the path was, now we turn to the vector of predecessors, pi. Right? And we follow this reconstruction by following them backwards. Writing this out in pseudocode is a bit ugly, but intuition behind it is actually really easy if you look at it visually. We have to backtrack from here, following the choices we took, right? So we end in 5. We follow the path. The predecessor tells us that right before 5 we were at 2. So I'm writing right to left, a 2. And then follow the predecessor again. What's the predecessor of 2? It's 1. And what's the predecessor of 1? Well, 1 is the starting node, so we're done. So I'm just backtracking by following these Sometimes they're called back pointers, you know, from back to front. And you see that I found the path, 1, 2, 5. So indeed, this is the correct one. We didn't get tricked like the greedy algorithm did. So hopefully this convinced you. If you want a proof, it basically comes down to the 3 insights from before. Because the algorithm is essentially just those insights put together. So this is the Viterbi algorithm. It can find us the weight of a maximum path from 1 to n in a DAG, as well as one such path with this weight by following the back pointers. So it's an algorithm that doesn't need like tricky structures, and as you can see, the implementation is quite simple. This is why it's a successful and like well-liked algorithm. You know, its memory layout structures are just like these arrays that have more or less the same shape as the graph that you start with. You'll see what this means when we look at some applications a bit later, but it's just for loops, so it's not like recursive calls or anything tricky like that. Right? It's fairly straightforward to implement, and it works. So its complexity comes from having one loop over nodes, and inside each of these loops, we have a max over predecessors. So if you count how many things here get maximized over, every edge will appear exactly once. Every edge is the predecessor, is one of the predecessors of some node in the DAG. So if you roll out these for loops, every edge appears exactly once. So that's why you have the complexity that is linear in both the number of nodes and the number of edges. Now, of course, we just did this example by hand on a very small toy graph. We have to see what happens when we start to design this sort of DAGs to represent more complicated problems, such as the ones that we actually will care about in practice. Have I convinced you, though, at least that the algorithm works, and that if I were to give you a DAG, this is an appealing way to find solutions in it? I hope so. I'm gonna show you next a couple of small extensions also still staying in DAG world, because we've seen how to find the maximizer, but how do we compute probability distributions over the paths? A weighted DAG can induce a probability distribution the same way as we did in the classification case, by taking the total weight of a path as the score of that configuration and normalizing all of them with a softmax. So if we wanted to calculate this, we can calculate the total weight of a path easily. It just requires traversing that one path and summing up the weights. So in this case, we have 3 paths. The weights are 30, 15, and 25. We can easily take the exp of those numbers, but in order to compute the probabilities, we need to normalize by the normalizing constant, right? So that's the catch for bigger and more complicated graphs. It's easy to compute one row of this table, but we cannot compute all rows easily in order to find the normalizing constant, because in the worst case, there could be very many, exponentially many such nodes. So we're gonna see that with an algorithm that is very much like Viterbi, we can also calculate this normalization constant, this denominator, efficiently, without having to explicitly enumerate all paths, because we're not always gonna get lucky and have a DAG with only 3 paths like this. Now, because these exps become really high numbers, like you also saw in this small example, it's usually good practice to work in the log domain. So that's why also the logistic regression loss is in log domain. So the probability of a path, which is the negative of the logistic loss, right, is the weight of the path minus this log sum exp, right? So what we are going to do next is compute the log sum exp directly, okay? We're gonna use the same insight as in Viterbi. The fact that any path can be seen as an extension of another path by one arc. And then we're gonna see that with this log sum exp, we can do a similar trick like the trick we did with max. If you have a constant plus log sum exp, then that constant can move inside. Basically, the addition distributes over this log sum exp operation. You can prove this yourself by taking exp in both sides and just verifying the equality. For now, if you trust me with this, that's enough. And now if, just like we had mi for the maximum of the path from 1 to I, now let's denote qi as the log sum exp over all paths from 1 to I. So we have an incremental definition of the log sum exp overall. We will derive a very similar dynamic programming recurrence as the one for max, but now for log sum exp. We have that qi is log sum exp over the predecessors of I. And if these predecessors are labeled j, then this log sum exp is over qj, so over the log sum exp of the predecessor, plus a single weight of the arc from j to I. If this got replaced by max instead of log sum exp, we would get exactly the dynamic programming recursion for j. So we just replaced max with log sum exp, which is a soft maximum. We can prove this using the properties that we've seen. We just once again break up the sum into two sums, one over predecessors, one over paths. And we use insight 4 to regroup by moving the sum inside the parentheses. And then we recognize that this term is exactly the definition, this definition, but with j instead of I. Right, so then this is just qj. Once again, I forgot how to write qj. And that's the proof. That's it. It's a couple of lines. Right? So once again, by rearranging the log sum exp over paths, by peeling back the final arc in the path, we recover log sum exp of the shorter subpaths, right, that are one step back, and we obtain this sort of nice one step back recursive relation. Very similar to the max case. So we can do exactly the same thing as we did for Viterbi. Notice that this time we don't even need back pointers. Right? This is called the forward algorithm. And once again, we initialized Q1 as 0 because log sum exp over an empty set, you can see that the right thing to put there would be a 0. And then we can fill this table one by one, just like we did for Viterbi. But instead of taking max over those paths, now we have to take log sum exp over them. That's the only change. The code is identical otherwise. Complexity is the same. And this algorithm lets us calculate the log probability of any given sequence efficiently, right? Because we get the normalizing constant, and once we have this, we can compute any probabilities of any sequence. Okay. And there's another very important trick that you can use then for learning. Like imagine that these weights come from some sort of neural network, the weights over our edges, right? If we want to learn them and have labels over which paths should have high probability, then we can maximize the probability of those paths with respect to the weights of the neural network, the parameters of the neural network that computes the weights. And this algorithm if you implement it in something like PyTorch or JAX or whatever, it's a bunch of stacked log-sum exp operations, so it's differentiable, right? So if you think of the W's as inputs to the algorithm, the probability is the output. Well, the normalizing constant, you know. So you can compute the logistic loss, just like we've seen. And if you plug this into autodiff, right, you will get gradients and you can learn. You just plug it in and it works, right? So this is all we would need in order to train some sort of machine learning model that is a probabilistic model of paths in a DAG when we know which paths we want to give high probability to. Okay? Things will become more concrete when we go back to applications, I promise you. Suspend that for a moment. It's coming. But while we still stay in abstract graph mathy world, I'm using this rabbit to denote kind of more advanced sections that you only need to go down the rabbit hole if you're interested in this. But there's a clear pattern here. We have two algorithms that are nearly identical, right? And what changed between them is we replaced the max with a log sum x, right? So why is this so samey? Even the proofs were almost identical, right? So if you've ever enjoyed an algebra course, you may have seen the notion of a semi-ring. So semi-rings are like general algebraic structures that kind of generalize the notion of addition and multiplication. So if you have this sort of set-like object over which you can define something that is plus-ish and something that is times-ish, if those operations satisfy some axioms, then it turns out they form a semi-ring. And if they form a semi-ring, Viterbi works on them, essentially. And the property has to do with that sort of distributivity, I think. In any case, this was a very exciting, very rich area of research because it lets you get like generic algorithms, like one kind of template algorithm that can apply for a bunch of different problems. And it was, for a while, a workhorse of NLP. It was a fan favorite concept. I do have some references if you want to dive deeper. So these are just two cases. Viterbi and log_sum_x are two possible semi-rings. But people have played around with things like top K semi-rings where you can still just do a single forward pass but get like top K solutions exactly. And there are many things in this world. Only if you want to go down the rabbit hole. A Boolean semi-ring, this is actually kind of going backwards. It's a simpler operation that only lets you verify path existence. There's an algorithm that lets you count paths and so on. So yeah, it's an elegant mathematical trick that turned out to be quite useful. It's always nice for some of us to learn about these. But putting this aside, so only go down the rabbit hole if you want to, of course. We now are armed with two great algorithms for dealing with path problems in DAGs. We can find the maximum scoring path, and we can do log_sum_x over all paths to compute the normalizing constant. I'm going to show you one third thing that you can do, and it also falls into this sort of framework very nicely. So if we built up to this point, why not add also this to our toolkit? We can sample paths, and not haphazardly, but I'm going to show you how to sample, so how to draw randomly paths from the distribution induced by the weights. What does this mean? So if we have a small enough DAG and we sample many paths, and we just empirically average how many times we saw each path, we should get exactly the probabilities, right? So these probabilities, right? So if in this DAG we would run our algorithm to draw like 1 million samples, the first path would appear 0.993 times out of a million. So we can draw paths proportional to the probability that the graph weights assigned to them. This can be quite useful in some cases. It allows us to do richer analyses. If you have a model that predicts a single output, you can talk about the one output that is good, right? But if you draw more outputs, if you can draw a bunch of samples, that you can talk about what is like a typical output, what is a typical path in this DAG. Is it the case that the maximizer is somehow very different from the typical path? Is it like a bit of an outlier in probability or not? You can also perform arbitrary inferences. For instance, you can compute the expectation of some function f of the whole path. These functions could be things like the length of the path, but it also could be like, I don't know, if our paths are some sort of paths over words, you could see how, like what's the probability that we would encounter the word cat, right, or something like this. So you could do this for arbitrary functions f. And this algorithm for structured sampling is also what you need for a fairly advanced topic called latent variable learning. So today, we of course only have time to talk about structured inputs and structured outputs. But there is a secret third thing, which is structured objects that are unobserved that you can model as a latent variable. So you observe pairs x, y, but you also want to do inference over some sort of hidden z that is structured. And that can be done if you know how to sample paths from an induced probability distribution. I'll show you how to do sampling by first considering the case of one arc at a time. And I'm going to do this for a general path ending in I. So if we want to figure out the probability that a path that ends in I hits node J right before finishing, so right before hitting node I, we can think of this as the probability of the arc Ji being last, given that the path ends in I. And we can actually calculate this without needing any information that is not local. We can just write this, so it's just a matter of manipulating the definitions a little bit. We can write this as summing up all cases, all weights of paths y prime concatenated with ji. So we sum over all paths of the form y prime and the arc ji. The exp of the score of those paths takes this form, right? And the normalizing constant is, of course, the sum over exp over all paths that end in I. Right? But if we rearrange this a little bit, we're going to notice that this term is constant with respect to j. No, sorry. This term is constant with respect to with respect to the w, basically. So it can come out of the log sum exp, right? So we can rewrite this as exponential of the weight of the one arc right at the end, factoring out over the sum of the exp over all the paths that end in j. And then the denominator stays exactly the same. And if you had the forward algorithm also on the screen in front of you at the same time, you would recognize these quantities as qj and qi. So these are quantities that are available when you run the forward algorithm. These are partial log sum exps over parts of the graph. And in particular, you can think of them this way. One of them is the log sum exp over all paths that end in j. The other one is the bigger log sum exp over paths that end in I, including this path, but possibly including others. So this allows us to compute exactly the probability of this arc ji being the last one, with everything else being readily available. So if we rearrange things a little bit inside the exp, we can simply write this as exp of weight of that one arc plus qj minus qi. So those are like adjustment factors. Right? So since all paths end in n, we can start from the end. We sample the final arc jn. How do we sample one arc? Now, instead of, we don't care about the total set of paths. We just sample one arc at a time. We consider all predecessors of the terminal node. We calculate this probability for each of them, and then we use like np.random.choice or something like this to draw from this categorical distribution, right? So we draw that arc, and then we repeat, right? But this time from the predecessor that we just drew. Now this resembles the backward pass of Viterbi when we followed back pointers. So you can sort of maybe think of this algorithm as stochastic back pointers. So in Viterbi, we picked the maximum every time, and we had a deterministic back pointer that we followed. Now we keep track of these local probabilities, and in the backward pass, instead of following a deterministic back pointer, we sample from back pointers that are weighted according to the probability of that arc. The algorithm looks a little different than that, but essentially you can think of it conceptually like a Viterbi with stochastic back pointers algorithm. So this algorithm is known as forward filtering backward sampling. I don't know why it's called that, but I guess it's because a lot of these algorithms come from, well, I'll tell you a bit more about naming and how horrible it is. But long story short, given the DAG, we first do the forward algorithm, exactly as I showed it to you a little bit earlier. But then we also do a backward pass that involves sampling. And this allows us to draw these sort of paths exactly according to the distribution that we want. So it comes almost for free, you know, on top of the framework that we are building. So we've seen that using this style of algorithms in DAGs that expand with one path at a time, then we can calculate the maximum weight path, the log sum exp overall paths, and also sample from the distribution. All of these in time that is linear in, you usually would call this the size of the graph, right? Of course, we're going to see a bunch of structures that fit this pattern, some that do not. There are some structures that are solvable by similar kinds of algorithms, but not representable as DAGs. I just want to keep this course less scary, so I didn't cover that. But there is a very slight extension of DAGs called hypergraphs. And in hypergraphs, an edge doesn't have to be between one node and one other node, but it can be between a bunch of nodes and terminate in a single node. It's just, it turns out with this sort of extension, all the algorithms still work, basically. But just the notation and everything will get so annoying that you would all hate me if you don't already. So there are a few more structured problems that cannot be represented by what I just showed you, but can be if you make this fairly small but hairy extension. And then beyond this, like I said, there are problems that cannot be solved at all with this kind of approach. Some of them can be solved with some other approaches, others of them can only be approximated. More details in my full course. This whole thing is called dynamic programming. Dynamic programming is, how much time do we have for this tangent? I'm gonna try and make a little bit of it, because just think it's weird and funny. So it's mostly credited to the work of Bellman in 1954. It's one of those popular enough concepts that it actually shows up even in like high school programming, like computer programming classes, which to me in high school was confusing to no end, possibly also to some of you. One reason for this is the programming in dynamic programming doesn't mean computer programming. It means some sort of like optimization, actually. It means coming up with the optimal schedule, let's say, for movements of logistics or whatever. There is a famous quotation. Was it from Bellman? I think it's a quotation from, or am I confusing that with with linear programming? No, I think it's Bellman that he came up with a name dynamic programming to attract funding, essentially, because nothing called dynamic could be wrong. You know, like it sounds, you know, so exciting and great, and then programming is useful, right? Because at the time, programming didn't mean computer programming so much, but it had this like more applied, even like maybe military sense. So it was very appealing to certain policymakers at the time. But then this quote is also considered possibly wrong, although Bellman himself said it, but there are he references some people in the quote that did not have the office that they were supposed to have at the time. If you look it up, you'll find some discussions about whether how real the story is. But what is definitely real is that this changed the name of these things forever, and now in high school we get confused about why this is called dynamic programming. It basically means optimization. It comes from fields like finding the best policy for a certain process, controlling of dynamical systems, and so on. That's the history of things. It has to do with stuff like reinforcement learning. But as we do it in NLP, and as I teach it to you in this course, the closest thing is Huang's tutorial from 2008, which was in a NLP conference, I think, calling, I don't remember exactly. So this is a great reference that actually follows modern notations that you would recognize. If you go up and try to read Bellman or try to read things from the 50s, 60s, 70s, it would be, to me, it's mostly unreadable, and you have to squint very hard to tell that these are actually the same things. But dynamic programming has been riddled with rediscovery, reinvention, and like generally finding the same thing under different names, because people in speech and people in like optimal codes and so on, they would often run into the same fundamental problems and not basically not find the existing work, right? So the popularity in NLP came via hidden Markov models in speech. There is a rich history starting at IBM Research and then through Bell Labs, and there's a bunch of key figures that worked on this heavily. But what I think is most interesting is that a lot of this work can only be found in a famous text called the Blue Book, which has not been circulated. You're going to find citations to it if you try to dig for the earliest work doing this stuff. For instance, if you're teaching a course and you want to tell the students about it, there are only like 4 copies of these blue books at various university libraries in the United States, so I couldn't get my hands on one. Maybe one day I will. If anybody wants to get me a birthday present, I would love a copy of the famous blue book that nobody circulated. Lawrence Rabiner gives a first-hand history. It's a very nice article about the history of dynamic programming and Viterbi and so on, including talking about this blue book, which was essentially the proceedings of like a closed doors workshop at Bell Labs or something like that. Anyway, Viterbi himself was working on information theory and codes, and the original algorithm is a special case of the one I showed you today. It wasn't initially for general DAGs, but for a specific problem. The term forward comes from Markov process literature due to Baum, and FFBS is framed with Shatner 1994. So you can see that even the range of years of discovery of these things varies widely, and at least these are the earliest that I could find. Maybe there is history I'm missing. So things have names that came from various different disciplines. Some people use Viterbi to talk about all of these algorithms when you change semirings. Other people say, no, that's Viterbi, that's forward. Other people don't even call it Viterbi unless it's for linear sequences. So naming in this field is a complete mess. I've tried to keep the names kind of simple and logical the best I could, but it can get very ambiguous. With that, let's look at some actual NLP application. First, we're going to do sequence tagging. Given a sequence of n items, x1 up to xn, and now this can finally become real. These can be words in English. Let's say that we want to label our words with part of speech labels. So we want to say that, for instance, the is a determiner, old is an adjective. So the sentence that I'm showing you here, the old man, the boat, is a famous, like, kind of garden path sentence where, as you read it, you might misinterpret it. You might think that it's talking about an old man, but then in fact, when you read the full sentence, that makes no sense, right? So one of these analyses is correct, the other is not. And I picked this sentence exactly because if you try to be greedy and just read the sentence left to right and pick the part of speech that makes sense, you will pick the wrong one, right? You would pick YA, when in fact, you should pick YB. Other examples of sequence tagging that you can solve with the exact same algorithm that we're going to see next involve some applications in speech, such as if you want to classify what phoneme is being said at each time step in a waveform file, or if you want to do things like, I don't know, optical character recognition by processing each label in conjunction to the ones next to it. Okay. So all of these problems take the same form. The input is a sequence of objects. The output is also a sequence of the same length. So different data points can have different lengths, and we have k possible output labels. So it's like classification, but at each position, right? So how many total possible outputs are there? We have k choices for the first slot, k choices for the second slot, k choices for the last one. So that is k to the power of L in the end, where L is the sequence length. So the longer the sequence, the more possible total assignments we have. So these are some example part of speech. This is a screenshot from Jurafsky and Martin's book that I've also been referencing throughout. So for part of speech tagging, we want to assign to each word one of these categories, let's say, that makes grammatical sense. Now, a simple way to do this, we also see that it's insufficient, is to assign a score for each part of speech tag at each position in the sentence, right? So you can compute a matrix of scores, for instance, with a neural network encoder that gives to each word in the sentence a score for every tag, right? We could do this. And then if you compute a total score of these, I was gonna do this by example, but there's no real point to calculate. But the score of YA is calculated by looking up the corresponding tags. Score of YB, you can see in this case it's a little bit smaller, right? So you could implement this sort of simple score fairly easily in PyTorch by just, essentially it looks kind of like applying a classifier at each position in the sequence. And in fact, we're gonna see that it's actually equivalent to applying a classifier in its sequence. What is the best possible sequence of labels with this sort of scorer? So the best possible label is the max over y1, y2, up to yn of the total score, but the total score is just a sum of scores for each tag. So we can easily move the max inside, and we have essentially a sum of the maxes of each row, right? So then the max of the score and also the argmax of the score can be simply done by finding the tags independently at each position in the sequence, right? The exact same thing happens once again, thank you semirings, with a normalizing constant. If you want to compute a log sum exp over all possible assignments of tags with this score that is just the sum of scores at each position, we have this log sum over 1, sum over 2, sum over n exp of a sum. And if we apply the property from before, we can move this we can turn the sum over j into a product, and then essentially this comes out, and we will get a sum over row-wise normalizing constants. This has an interpretation probabilistically too. This means that the variables corresponding to each tag assignment at each position are independent of one another, because the log probability of the whole label sequence, so the whole sequence of assigned part of speech tags, which by definition is the score of the sequence y minus log sum x over all other sequences. And if we apply what we've just derived, this turns into the sum of row-wise, like the sum of the probability of each tag at each position, right? These are in log, but if we take exp, then this shows us that the probability of the joint assignment is the product of the probability of each assignment. So it turns out that what we did is inadvertently bake into this model an independence assumption, right? By choosing our scorer to factorize this way, so to sum over tags in this way completely separately of one another, okay? So for now, we don't need any algorithms. This is just, if you want to train a model like this, in PyTorch, you would essentially have a classification loss, but applied n times, one for each word in your sequence. And this is a fine algorithm to use. It's fast, right? And you are indeed learning to predict tags for each word in your sequence. But you should be aware that you baked into it this independence assumption, right? And here it is, right? This is why it turned out this way, right? What are we missing with this assumption? And what would be the opposite, let's say, right? What would be a richer score that maybe would not manifest this independence assumption? So one that would fully take into account the sequential structure of y. And I want to kind of, for a moment, fantasize about what the complete opposite would be. The fully global scorer. Remember, go back to the jockey horse assignment problem, right? So what if we enumerate every possible structure, right? So in this case, every possible configuration of tags, and we have some way to assign scores to these tags. What happened last time? We chose our score to be just a sum of the parts, and that turned out to be too simple. What if we don't make any assumptions, and we just let that score be defined, I don't know, in some arbitrarily complex way, right? This would be the most expressive possible classifier. This could be a classifier that, for instance, picks out any combination of tags with a specific rule that could not be expressed just as a sum, right? Like if we express it as a sum, then you could have, for instance, a sequence that starts with a verb, if you permute, for instance, the tags and the verbs at the end, the sum would be the same, right? But with this sort of fully global parameterization, you could have special cases for like anything, essentially, right? This is as expressive as possible. However, the only way to do any kind of calculations or learning would be if we could actually enumerate that full table. So in general, we can't, right? But I want you to just kind of see that these are opposites in some sense. One of them is fully local. The scores are only at the level of one word, one tag. The other one, the scores are completely unrestricted, but that also doesn't give us any handle to grab it from and solve the problem, right? So how do we get something in between, like some sort of middle ground that is both expressive and tractable, so we can have algorithms for it? In a sense, this is the whole riddle of structured prediction, right? It's finding a representation that is not too rich, not too poor, right, in terms of representation power, so that we can deal with it with algorithms, right? But also it's useful enough for our problems, for our analysis, and so on. For sequence tagging, what we're gonna do is score not just with decomposed scores for each position, but also with transition scores for consecutive tags. We're gonna see that this breaks the independence assumption while still giving us a scorer that leads to tractable algorithms. So the first term in the score is the same. It's a score for every position and every tag. But then we have a second term that is a score for every pair of consecutive tags. See? So if we have a sequence like noun, det, verb, this first part of the score would be the same as in the simple case, but then we additionally have a score for the sequence noun, det. So this is kind of a reward that you get if you think that it's nice and good to have a noun followed by a determiner in your sequence. And if you think this is not good, then this score might be very negative. And same for like determiner verb. In this case, these are maybe fairly unnatural things in the English language. It's more likely to have determiner noun than noun determiner. So maybe in this case, this will allow you to downweight an analysis, right? Because of some sort of unnatural ordering that can be learned. See? Oh, here there was a type, but here it's fixed in the sum there. So the tag scores are like the local classifier. This can be computed just as before. So to implement this, you can run any kind of sequence encoder and have like a linear softmax or something kind of layer at each position, right? Not softmax, just a linear layer that computes k-scores for each tag at each position. How do we compute the transition scores? And now you have a bunch of modeling options once again. You'll see that for algorithms, this actually doesn't matter. You just will take the k by k matrix T as an input. One simple way to do it is to just have a learned parameter because its size does not depend on n. So this is k by k. It just depends on the number of tags. So you can learn a single matrix like this as a parameter of your model that will kind of learn which pairs of tags T1, T2 are likely to come in that specific order and which are not, right? So that's one way to parameterize this. And you can go even further and have these transition scores actually depend also on X. So you can read the sentence and then based on that, you might give a different transition matrix. As an example of where this might be useful, imagine that you're trying to train a model that predicts part of speech tags, but not just in one language, but in different languages. So you could imagine then that you have a subcomponent that predicts what language you're looking at, it will give you a different transition score table for each of those. So this is something that is entirely possible within the framework that we're discussing. The only thing that matters is that we are able to compute this score and that we are able to do the things from before. So the max and the log sum exp. And I will show you that we can. We put it in the form of a DAG, right? And now because we went through the pain of deriving the algorithms 30 minutes ago, now this is all you need to be convinced that we have the algorithms and they're available, right? How do we form the DAG? The hieroglyphs here are like a little bit weird, but I think the picture on the left makes it a bit clearer. So this is a repeatable construction of a DAG that can work for any sequence and for any set of tags. I'm arranging them into rows, so one row for every possible tag, and one column for every position in the sequence. And we are adding two additional nodes, a special start node and a special target node. So I'm going to label this S and label this T, and we're going to look for paths from S to T. Okay? And now, how are we going to weigh these edges in the DAG? Well, any edge that goes into a node JC, it means that when you follow this edge, you are assigning tag C at position J. So what should be the reward that you get for making that assignment? Well, the reward should contain the score itself of JC, of putting label C at position J. So this comes from the classifier term. This comes from the separable term that says the word old is often an adjective, right, or something like this. This comes from there. But then you also add to this weight the transition cost of C prime C, where C prime is the node you're coming from, right? So this is where the power comes from, because we have edges. The weight of an edge, we can pick it to depend on both the first and the second node in the edge. So, for instance, a sequence like determiner, noun, verb, determiner, noun would look like this in the DAG. We always start here, determiner, noun, verb, determiner, noun, and into the terminus, right? And you can see that every edge can give us a reward that depends not only on the current assigned tag, but also on the previous tag, right? So that allows us to have this transition-based richer score. It's a DAG. This is how to construct it. This is how to assign the weights. You can see that the total reward, the total score that you get for a path is exactly what I promised it would be when we designed the scorer. And I already drew it in topological order. You see all of the edges on the screen go from left to right. So you can only have nodes between, sorry, you can only have edges between this slice of nodes and this slice of nodes, but you cannot go backwards in them. So in fact, there are many different topological orderings, because you could process these in any order you want, but you have to finish all of these before you go on to these, before you go on to these, and so on. So it's already built in topological ordering. It is a DAG, and if we count the size of the DAG, we see that it is, so remember, the complexity of the algorithms was bounded by the number of edges. And in this case, the number of edges is the length of the sequence times k squared, where k is the number of tags. So it's quadratic It's no longer linear in the number of tags. But quadratic is much more manageable than how many tags were there? Sorry, how many sequences were there compared to? If we wanted to enumerate all of these, it was k to the power of n. Okay, so that's a lot worse than nk squared. So because we can put these in the form of a DAG, and because the DAG is small enough, then we immediately get all the algorithms we need to train this sort of structure prediction model. We need the Viterbi algorithm. So if you instantiate the general Viterbi algorithm for the form of this particular graph, it will take a form that is maybe the most widely known form of the Viterbi algorithm. Essentially, you loop over the sequence from 2 to n, and then for each tag, you take the max over all possible previous tags, right? So essentially what this means visually in the graph is for every node here, you will consider all of its predecessors, pick the maximum, and record the back pointers that you came from, right? And then on the way back, when you eventually get to the target node, you follow the back pointers and you will find your optimal sequence. I did nothing but translate the general Viterbi algorithm onto the DAG that is drawn on the screen. All I had to do here is a little bit of careful index renaming, essentially, right? But it's the exact same algorithm. How would this look like as an example? So remember that we have our so-called unary scores. This is the decomposable part. This is the classifier part of the model. And then let's also have some transition scores that now tell us what pairs of tags are more natural in a certain order. Okay? So now let's do the algorithm one by one. We're gonna first copy the first row as it is, because there are no arcs coming into it except just the source. So just like before, the first step is usually easy, right? Now for the second row, imagine the DAG in your head. I'm drawing these arrows to kind of help you. You have to pick, if we want to give the label determiner to the word old, we have to consider all 4 possible directions that we could have come from to get here. So those directions correspond to having had determiner, noun determiner, adjective determiner, or verb determiner. So they correspond to this column of the transition matrix, essentially, right? So when you consider the possible previous tag alongside, like you have to also add to it how likely the classifier thinks that determiner is at that position. You add them all up together and you pick the best one. And the best one is 1 plus 0. Okay, so that's why I filled in a 1 there. I'm going through it a little bit fast, but essentially we have to add this number with all of these 4 numbers and pick the best out of the out of the resulting list. Okay. So because the best was the verb here, then I didn't draw this, but we should also store a back pointer that looks like this, essentially. We have to say, if we put the tag that at position 2 here, then the back pointer that we must have come from has to be from a previous verb tag. Right, so this is the Viterbi back pointer, nothing else. You repeat this process for the next position. So this time what do we have? We have old to be noun. It gets a score of 1. But we have to consider this column. So I think then the answer should be 3 plus 1. Oops. I think the answer, oh sorry, 3 plus 1 plus we have to add up whatever we came from, so it's 4 plus 5, so it's 9. Because we're accumulating the total score of the path up to here. So as you repeatedly fill up this table, you will eventually have the maximum weight of any path that completes the full sentence. So at the end, you have to just pick the maximum in the last row, because everything terminates into the target node like this. So we have to pick the 26 there, and then following the back pointers that I didn't draw as we were going, but they are there, we can find the optimal assignment. So this is how we can do Viterbi and find the optimal scoring sequence of tags, including transition scores. Now, of course, we also have the forward algorithm to compute probabilities, and that uses the log sum exp form of the recursion. It takes this form when you actually plug in the values. And I have a worked example here that kind of shows you. So remember the maximum was 26. The log sum exp, which is a soft maximum, is 26.88 in this case. This is too complicated to do by hand, I think, because of all of the logs and exps, but I have it worked out here for you. Also, this is an example of how you can use now the forward algorithm to compute probabilities. The probability of sequence YA is going to be exp of 25 minus 26.885. So you can calculate it like this. The log probability is minus 1.885. If you take exp of this, you will get the probability of the sequence. If you had enough time to do this operation for every possible sequence of tags, the k to the power of n possible ones, if you sum them all up, they would sum to 1. And that is actually a good way to check that your implementation of the forward algorithm is correct. So you can also use this to compare log probabilities of various choices. Putting this all together, we have all the ingredients needed to build and train a probabilistic sequence stagger with transition scores. Okay? Receive an input sequence X. Use some sort of neural network or handcrafted features or anything in the world you want to compute the matrix A and the matrix T. Now, at testing time, you run Viterbi, it gives you the predicted sequence, you can evaluate, see how well it did. At training time, run the forward algorithm, compute the negative log probability of the gold sequence, and optimize, take a gradient step. Those are all the building blocks needed to train a structured sequence stagger. Now let's go to the next application. I'm going to show you sequence segmentation, which is quite a different challenging problem, and you'll see it falls into the same framework. I like to visualize the sequence segmentation problem as cutting a rod. So this is actually how it's discussed in the famous algorithm books from Corman et al., CLRS. Let's say you have a rod made out of some precious metal that has length n, and you can cut it along every marker. So you can cut it like at 1 centimeter, 2 centimeters, up to n. But the value of each cut is not the same. Every cut has a different value, maybe because of properties of the metal. What are the best cuts to make in order to maximize the total value of the pieces that you get when you're done? This is kind of, an abstract, not really real problem, but it maps to a lot of actually real problems. If you think of each of these segments corresponding to a nucleotide in a DNA or RNA sequence, then you might be asking, what is the best way to chop up this DNA sequence into analyzable subparts? If you're talking about, let's say, Japanese characters, because Japanese language doesn't use spaces to delineate words, you might wonder what is the optimal segmentation of the sequence into some notion of words that we might want to analyze. If we are dealing with English text that maybe is already separated into words, what if we want to identify which segments in here correspond to entities that we might do some analysis on? If our input is a waveform of speech, what if we want to separate it into, I don't know, different phonemes? When does each phoneme start or end? These are just a bunch of possible applications of the sequence segmentation problem. Just like in the case of tagging, we have to first figure out what is the problem itself, formalize it, give it like names, and design a scorer. Once we know how to score things, then we can move forward and design algorithms for it. So one way to look at this is where we make the cuts. If, for instance, in this sequence, we make the cuts at 4 and 5, the resulting segments are 0, 4, 4, 5, and 5, 10. A small aside here, I'm using a numbering system that might be confusing if you haven't seen it before, but it's super, super powerful because in this sort of algorithms, you are gonna have so many off by 1 errors. The numbering that I'm using here on the slide is called fence post indexing. Notice that my indices are not below each letter, but rather in between. I am numbering not the words themselves, or not the items themselves, but the gaps between them, the fence posts between them. So this makes a lot of the index math a lot easier. We start at 0, we end at 10. That means we have exactly 10 items in the sequence, not n-1 or n+1, exactly n. And then the segments start and end at these in-between spaces. This is sometimes called like interstitial indexing or something, but fence post indexing is maybe a bit more visual. It's very helpful. Sometimes the difference between spending like weeks on something, on an implementation, and hours is finding the right way to count things in it. Okay, so if I make a single cut at position 6, I am left with segments 0, 6 and 6, 10. If I make every possible cut, 1, 2, 3, 4, 5, 6, 7, 8, 9, I get segments 0, 1, 1, 2, 2, 3, dot, dot, 9, 10. One thing that the students who take my class always get confused with is the difference between a segment and a segmentation. A segment is a possible unit, ij, like this. Right? A segmentation is a combination of segments that glue together in a valid way, you see? So how many possible segments do we have? Do I have the answers on the slides? I don't. How many possible segments we have? So segments are all pairs of the form ij with, so I could be 0, j could be n, but I and j cannot be equal because segments must have length at least 1. You cannot have an empty segment. So these are all possible segments, okay? So you can count how many of these there are. I always get it wrong when I do it. But the way you would do it is, okay, for I equals 0, you have how many? We have 1, 2, 3, up to n. So we have n segments. For I equals 1, you have n-1 segments. And eventually for I equals n, we have 0 segments. So then we have the sum. This is the total number of segments. What is this sum? I always get it wrong. It's on the order of n squared, but it's less than n squared, right? It's Yeah, so what I always get wrong here is whether it's minus or plus. I literally never get this right. So what you can always do is kind of check. So what happens if n is equal to 4? So we have the possible segments 0, 1, 0, 2, 0, 3, 0, 4, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, 4, 5, 6, 7, 8, 9, 10. 10 segments. 4 times 3 over 2 is wrong. That would be 6. So this is a plus, right? I had it wrong. That's how you check. How many possible segmentations? So yeah, the answer was n squared and a little more, right? How many possible segmentations do we have? How do we answer this? This is a little bit trickier to answer. It's very hard to actually figure out which segmentations are compatible or not. And if you try to do it that way, you'll not get anywhere. But you can be a little bit clever and repose the question in terms of cuts. What are the possible cuts we can make? At each of these positions, you have a binary choice. Either you make a cut there or you don't, right? So each of these choices leads to a different set of segmentations, right? So in other words, we have 2 times 2 times 2. How many times? 9 times. So it's 2 to the power of n minus 1. This is the number of total segmentations. You can think of it in terms of cuts. Okay. So exponentially many segmentations, quadratically many segments. This makes it already seem that that we are kind of in a nice dynamic programming universe. Indeed, if we assign a score to every possible segment ij, you can view this as the upper triangle of an n plus 1 by n plus 1 matrix. Okay, so this upper triangle corresponds exactly to what I drew here. Wait a second. 0, 1, 0, 2. Yeah, exactly. This is 0, 1. This is 0, 2. It corresponds exactly to what I drew there. So what we need is, once again, some sort of neural net or linear model or whatever to give us a score for every possible segment, not segmentation. So there are only n times n plus 1 over 2 possible segments. Not too much. The upper triangle of a matrix. We can handle this on our computers, right? Now, once you have these scores, let's build a DAG to represent segmentations. Let's put a node at every fence post. So our nodes are 0, 1 up to n. And we have every possible segment as an edge. Note this is a DAG, right? So our edges only go from left to right. We have the edge 0, 1, the edge 1, 2, but also the edge 0, 2, and so on. So you end up with this nice circular mesh. Right? So these are exactly the segments. What is the topologic order of this DAG? All edges already go from left to right if I number them this way. So it's already given in topologic order. Any path that starts here and ends here, notice it corresponds to a valid segmentation of the sequence. We can take the path 0, 5. This corresponds to making no cuts at all. We can take the path 0, 1, 1, 2, 1, 3. This corresponds to every possible cut, and so forth. Okay? So there you have it. Viterbi algorithm. It just comes, you crank it, right? It's exactly the algorithm applied to this indexing scheme. I'm not even going to bother. You can do the forward algorithm. You can check it out numerically. But because it's a DAG, because you can apply the construction exactly as I showed you. This works. You can trust me on it, right? So we got a segmentation classifier. We can compute probabilities. We can train it, right? Many people don't know this. So there are extensions that you can make to this sort of thing. Bounded segment length. If you want to make this a bit faster, you can say, for instance, if you know in your data there are no segments of length more than L, which is maybe much less than the sequence length, it corresponds to discarding some edges in the DAG like this. So then you can handle longer sequences. How does this impact the complexity? You can try to solve this as an exercise. If you want to have labeled segments, but still scoring be separate per segment, something very simple happens, because if you have multiple labeled arcs like this between the same two nodes, you can actually just pick the best one before you even run the algorithm. So nothing really changes. It's like you pick the best label for every segment, and then you run the previous algorithm with those edges selected. There is a bit of a more complicated extension where you can have labels for every segment, but you also want to score transitions between consecutive labels. So this would be a combination of like the DAG that we had for Viterbi and the DAG that we have for segmentation. It's an interesting exercise. We're not gonna do it today. Okay. The summary is we have on the order of 2 to the n possible segmentations, quadratically many segments. So dynamic programming lets us have efficient, so quadratic time classifiers, probabilistic models of segmentation. And we saw a few extensions of this stuff. I have a bunch of more historical notes here because once again I went down rabbit holes. This model, the model for sequence stacking is sometimes called linear chain CRF. It's sometimes incorrectly just called CRF. I don't think this name is super helpful. It's very technical and it doesn't really say what it is. The first iteration of the segmentation model that I've found is Sedgwick, but you actually cannot find this paper online because the IEEE archive has it misscanned, and I emailed them about it, and they said there's nothing they can do. This is also, like I said, a rod cutting problem is in Corman et al., but there are no references. So this algorithm has also been reinvented, rediscovered a bunch of times. In fact, it is efficient, it is polynomial. I could rant about this, but we are short on time, so I want to talk about evaluation before we're done. Evaluation is very important in machine learning, right? And just like learning becomes a bit trickier with structures, so does evaluation. If you don't know, remember the notation of the Iverson bracket. We can write like this between brackets p to mean 1 if p is true, 0 otherwise. How do we evaluate just simple classifiers? One metric is accuracy, which can be interpreted as the fraction of test cases that are correctly classified. All right? This can be written with Iverson notation like this. You may also be familiar with precision recall and F1. Precision, given a class, precision is a fraction of the test cases correctly predicted as class C. So they must be a part of class C and they must be correctly predicted. Recall is the number of test cases, the fraction of test cases from class C that are correctly predicted. So how many do we get back out of the ones that are really from class C? Okay, and the F1 score is the harmonic mean of precision and recall. For binary classifiers, it's usually intuitive to just compute these for the so-called positive class that you want to detect, right? And it may be useful to think about precision recall and F-score in terms of this confusion matrix. So for each class, you can have the true positives of that class, false positives, true negatives, false negatives. And you have the corresponding expressions for precision recall and accuracy. Then to combine these over classes, you can macro average, micro average, but there are a bunch of tricky things to take into account here. In some cases, it makes more sense to have an unweighted average. In other cases, to have an average over weighted by frequency. So this is already complicated in the multi-class classification case. When we move over to sequences, it gets even trickier. For sequential data, even accuracy becomes more complicated. If we apply accuracy as is, we would get a form of sequence level accuracy, in which we would count as correct if we got the whole sequence right, and otherwise we would count that as a 0. Okay? So for this example here, with these two sentences, I made one mistake here and one mistake here, but if we calculate sequence level accuracy, they are both wrong, so we have 0 over 2 accuracy in total. Right? But we can also do a tag level accuracy, which basically means treating each position as separate. Right? And in that case, we made 2 mistakes, so we only have 4 over 6. These are way different, and they tell us different things. So yeah, usually tag level accuracy is used for a part of speech tagging. You can also do a precision recall F1 score at tag level like this. Now, for segmentations, things also get super interesting, because for segmentations, we cannot even think of accuracy in the same way, because the gold segments and the predicted segments could be sets of different size, right? So imagine here, like here we have 1, 2, 3, 4 gold segments, and the prediction set is only 3 segments. We cannot even compare them really, right? On the other hand, well, yeah, we can talk about cuts. That's not a recommended idea. But I want to show you the, let's say, correct or at least traditional way to do this. And that is segment level precision recall and F-score. Looking at the sets of gold and the sets of predicted this way, we can count true positive. So which segments appear in both? False positive as which segments appear in one but not the other. And same for false negatives. And you can compute precision and recall using those ratios. And in this case, you'll see that both are 0, even if you see one cut was correct, but no segments here were correctly retrieved. So the correct thing here, or at least with my intuition, is to say 0. Right? If we have labeled segmentation like happens in named entity recognition, then you can think of additionally having to every segment tuple also a label like this. And the evaluation is exactly the same. We calculate true positive, true negative, false negative. Sorry, not true negative. True pos, false neg, and you can compute precision and recall exactly the same way. So basically you treat the label as part of the object. So if you want to count it as a true positive, you must correctly retrieve everything. Label, start, and end. Otherwise, it's a negative. Right. So this is the standard way to do evaluation for chunking, named entity recognition, and so on. It's also possible to do it maybe per class, but it's not really standard. And as an interesting aside, an annoying thing that happens in the structure prediction thing is that you cannot actually usefully think of accuracy metrics here, just precision recall and F-score. And why is that? Remember, for accuracy, you need true positives and true negatives. So in this case, true negatives are all of the possible segments that do not appear in either of the two. But there are so many of these, right? Like, for instance, Armstrong visited with the label of person is a true negative. So almost all segments are true negatives, right? So that means if you try to compute accuracy, you would get, 99% sort of numbers. So it's not at all useful. That's why we use precision recall and F1 for this sort of problems. And here we are at the end. So today we've talked about predicting structures. Structured objects are objects that are made out of smaller parts, like tags, arcs, and so on. They're parts that interact with each other in large possible number of combinations. This combinatorial nature of structures makes evaluation and learning more complicated, but they also give us rich, powerful, useful representations. We've seen how to encode structured objects into vector representations, and we've seen how to predict structures by representing them as paths in a DAG with dynamic programming algorithms. And we've seen two applications, sequence tagging and segmentations. Thanks. I think we're good for time. It's a little over. Thanks, everyone.
Maybe we can take one or two questions and then discuss. We'll speak over lunch. Any questions?
Thanks for the talk. It was really interesting. I had a question about the first part of the lecture about node embeddings for the graphs. So if this is an iterative process over nodes, I wonder how it is calculated for directed graphs. And if in this case you would have a kind of information leak where there is nodes that have no edges coming into them, and how you can deal with this when you calculate the embeddings for the nodes.
So you're talking about this slide, I think, right?
Yes.
Yeah, indeed. So if the graph, the term for this is connected components, and if there are if the graph is not connected, then it might have several components that are isolated from one another. And indeed, if you do this, there would be no exchange of information between those components. But the question is, if you are correct about the graph structure being like this, then isn't this the right thing to do, right? Like there really shouldn't be any passage across something that is not connected.
I'm sorry, I meant a directed graph where like a node has information coming out or in, but maybe some nodes only have incoming edges and no outgoing edges, or the other way around.
Oh, but still, we're still talking about inputs.
Yes.
Yeah. No, that's a good point. So if we were doing this on a directed graph, then it's much more likely to have, you'll have fewer neighbors. Yeah, indeed. I would say that's a good observation. The information in that case, in the directed case, will only flow in the direction of the arrows. But then I guess there can be a difference between what you consider the directed graph and what graph you actually do message passing on. So what I have seen in NLP applications for people doing, for instance, various sort of classification on top of dependency graphs and things like this, is you do start with a dependency graph that is directed, but you pass messages also backward, like with a different sort of matrix, right? So here you have a message from neighbors. In the directed case, this would be, let's say, incoming neighbors. And then you could also have W out neighbors. And this would be, instead of M, I'm going to call it NI, something like this. So I've seen this done. It's basically you are doing message passing, but not on the directed graph, but let's say on the backbone of the graph, but with different weights, depending on whether the edge goes in or out. And I guess they found that worked better there. I would say that you just can think of that as a variation of the model, right? If you think it makes more sense to pass things in both directions. But there must also be cases, I don't know specific applications, but there must be cases where it makes more sense to just follow the direction as it is. For instance, where the graph follows some process that really works like that, Right? There's a question also in the back.
Yeah, hi Vlad, thanks a lot for the talk. One question in the part of speech tagging, you mentioned of the option to learn via backpropagation the transition probabilities, right? Mm-hmm. I was wondering if this really buys you something and you can just instead follow the standard approach of counting as we do, let's say, with n-grams, and fix them like that based on your training set, possibly with adding some constraints rather than learning them via backprop, right?
Yeah, that's a great question. I kept things kind of, I think thinking that, sorry, like being aware that you can train them by backprop lets you think of this whole thing as modular, right? Like no matter how you define those scores and those transitions, you can optimize exactly that loss by backprop, right? If the transition scores are fixed and stationary, which was the example that we used here. So if you have the same matrix for every data point, right, shared, then I think indeed you can get either optimal or if not very close by just counting these, because they are sort of separate from the classification case. That might not be case. They might not be exactly optimal, but it's definitely a good initialization. Right? It might not get you minimum training loss. I'm not sure. I never thought about that specifically. But yeah, it is common practice to initialize them based on weighing, but based on like counting. But this does interfere with the other part of the term. But in general, those scores don't have to be a stationary matrix. They could be a function of x. They could be non-stationary, so a function of at each position they could be different, right? So in that cases, you would need to learn them with some sort of gradient descent.
Sorry, we need to stop here because we are running out of time. But
thanks, everyone.
You get a present,
Thank you.
And we thank you very much.